Have you ever thought about going to the sun? While it might sound impossible, NASA engineers have done it. Interested in how? Stick around to find out. In the vast expanse of space, a daring mission was launched, one that would take humanity closer to the heart of our solar system than ever before. The Parker Solar Probe, an engineering marvel of modern space technology, was born from the dream of unraveling the mysteries of our closest star, the Sun. Launched by NASA in 2018, this advanced spacecraft was on a mission to venture into the outer corona, or the atmosphere of the Sun, a region bathed in immense heat and radiation. This remarkable endeavor aimed to push the boundaries of our spacecraft technology and expand our understanding of solar physics. The probe was named after Eugene Newman Parker, a renowned solar and plasma physicist. Let's take a deep dive into this remarkable mission to the closest star, the Sun. Do you think it's possible to touch the Sun? If you think it's impossible, just stay here. At the heart of the Parker Solar Probe's mission lies a simple yet profound question. What powers the Sun's outer corona, and how does it shape the dynamics of our solar system? Equipped with an array of cutting-edge instruments and sensors, the Parker Solar Probe pioneered a bold journey into the Sun's lower corona, where it mapped the environment, as well as the energetic processes driving the solar wind and particle acceleration mechanisms. Could you imagine that something built by humans could survive the intense heat near the Sun? Well, this was probably the greatest challenge NASA engineers had to solve. To withstand the intense heat and radiation near the Sun, the spacecraft employs a formidable heat shield. At perihelion, solar radiation reaches a staggering 650 kilowatts per square meter, a staggering 475 times more intense than in Earth's orbit. You might wonder, what is perihelion in all these terms? When talking about a spacecraft's orbit, we cannot use maps or any standard methods of locating something like here on Earth. Objects in space orbit each other in an intricate and sometimes incredibly complex way. Scientists use certain terms to characterize these orbits, and the two most important pieces of information are perihelion and aphelion, or perigee and apogee, if the object is orbiting the Earth. Perihelion is the lowest point of the given spacecraft's orbit, the closest it will get to the Sun, while aphelion the highest point in the orbit, thus the farthest point from the Sun in Parker Solar Probe's case. But what are the immense temperatures the solar probe has to endure every time it flies close to the Sun? This hexagonal shield, measuring 2.3 meters in diameter and 11.4 centimeters thick, boasts two panels of reinforced carbon-carbon composite with a lightweight carbon foam core, designed to endure temperatures exceeding 1,370 degrees Celsius or 2,500 degrees Fahrenheit. Remarkably, this shield, weighing a mere 73 kilograms, maintains the spacecraft's internal temperature at a comfortable 29 degrees Celsius or 85 Fahrenheit. Crafted with a white reflective alumina surface layer to minimize absorption, the shield serves as a crucial barrier between the spacecraft and the Sun's harmful radiation. Positioned on the Sun-facing side, it creates a shadow under which the spacecraft's systems and scientific instruments are housed, shielded from direct solar radiation. Just to put it into perspective, that temperature and heat is comparable to what's inside modern steel working foundries, and NASA built an entire spacecraft to work in these conditions. Crazy, isn't it? Without this shield, the probe would succumb to damage within moments. With communication delays of about 8 minutes each way, the Parker Solar Probe operates completely autonomously, relying on 4 light sensors to detect the earliest signs of direct sunlight breaching the shield's limits. In response, it swiftly adjusts its position using reaction wheels, ensuring it remains within the protective shadow. This level of autonomy marks the Parker Solar Probe as one of the most self-sufficient spacecraft ever developed by humanity. Powering its mission is a dual solar panel system. It would be a bit ironic to use a different type of power generation, wouldn't it be? A primary array, used beyond 0.25 astronomical units, or roughly 23 million miles, retracts behind the shadow shield during close solar encounters. Meanwhile, a smaller secondary array is equipped with pumped fluid cooling system, which sustains power during the spacecraft's closest approach to the Sun, maintaining optimal operating temperatures for both the solar panels and the scientific instrumentation. The Parker Solar Probe mission uses Venus's gravity to assist it in lowering its orbit to approach the Sun. By flying by Venus 7 times over 7 years, the probe's orbit around the Sun gradually decreases, bringing the probe as close as about 8.5 times the sun's radius, or roughly 3.2 million miles from its surface. But this close journey exposes the spacecraft to intense radiation, which can cause problems like charging effects, damage to materials, and interruptions in communication. Did you know that the Parker Solar Probe was launched on one of the most powerful rockets ever? To launch the probe into this challenging orbit, it needed an insane amount of energy. It launched into space aboard the Delta IV Heavy, one of America's largest rockets, assisted with an extra boost from the Star 48 single-use motor. As the probe circles the sun, reaching incredibly high speeds up to 120 miles per second, making it the fastest object made by humans. In fact, on September 27, 2023, it reached a mind-blowing speed of 394,736 miles per hour, which could get you from New York to Tokyo in just over a minute. As it gets closer to the sun, gravity speeds it up, but as it moves away, it slows down until it reaches its farthest point from the sun, or aphelion. The goals of the Parker Solar Probe mission encompass tracing the energy flow within the sun's corona and the acceleration of the solar wind, understanding how energy moves from the lower solar atmosphere to the corona and solar wind, investigating the processes shaping the velocity distributions in the heliosphere, and examining how corona processes influence solar wind properties. On November 6, 2018, the Parker Solar Probe made a significant observation during its mission. It encountered its first magnetic switchbacks and sudden reversals in the magnetic field of the solar wind. These intriguing phenomena had previously been observed by the NASA ESA mission Ulysses, which was the first spacecraft to fly over the sun's poles. This encounter marked a milestone in our understanding of solar dynamics, providing valuable data on the behavior of the solar wind close to the sun. Following this, on December 4, 2019, the Parker Solar Probe made its initial dives near the sun, resulting in the publication of the first 4 research papers detailing the findings. These papers shed light on various aspects of the sun's behavior, including the direction and strength of its magnetic field. What's more, the spacecraft not only detected magnetic waves and charged particles but even took photos of it. We can see small parts of the sun zipping by in the vast expanse of space. One notable discovery was the frequent and short-lived changes in the direction of the sun's magnetic field, providing crucial insights into the mechanisms underlying the coronal heating problem. The probe's measurements confirmed the hypothesis that Alfvén waves play a significant role in this process. Hold up! What are Alfvén waves? Imagine you're at a beach watching waves smoothly roll in. Now picture something similar happening in space, but instead of water, it's a super hot electrically charged gas called plasma. And instead of beach sand, there are magnetic fields weaving through it. Alfvén waves are like ripples in this space plasma, but they're special because they're caused by the ions, charged particles, and the magnetic fields bouncing around. Picture the ions and magnetic fields doing a cosmic dance together, creating these waves as they move. Now, unlike regular ocean waves that can go in any direction, Alfvén waves travel along the magnetic field lines. It's like they're surfing along these invisible highways in space. But here's the twist. Even though they're cruising along the magnetic field lines, the ions and the magnetic field itself jiggle side to side as the wave moves forward. Studying Alfvén waves is crucial because they play a fundamental role in understanding how energy and momentum are transferred in space, particularly in environments like the sun's atmosphere, Earth's magnetosphere, and even in astrophysical phenomena like pulsars and black holes. Additionally, the Parker Solar Probe detected around 1,000 rogue magnetic waves in the solar atmosphere, which had the remarkable ability to instantaneously increase solar winds by as much as 300,000 miles per hour, and even completely reverse the local magnetic field. This discovery highlighted the dynamic and complex nature of the sun's magnetic environment. If you thought the list ends here, you are wrong. There is more science. Another noteworthy discovery made by the Parker Solar Probe was the existence of a cosmic dust-free zone extending 3.5 million miles radius from the sun. This phenomenon was attributed to the vaporization of cosmic dust particles by the intense radiation emitted by the sun. During its 8th flyby on April 28, 2021, the Parker Solar Probe reached a significant milestone when it encountered specific magnetic and particle conditions at the distance of just over 18 times the radius of the sun, indicating a potential penetration of the Alfvén surface. It's like a boundary around the star, where the heat and pressure from the star aren't strong enough to hold the solar material in anymore, so it starts blowing away as solar wind. So it's where the star's atmosphere ends and where space begins. This event, described by NASA as one marked a significant achievement in solar exploration. Overall, these discoveries made by the Parker Solar Probe have significantly advanced our understanding of the Sun and its influence on the solar system, paving the way for further exploration and scientific inquiry. We hope you enjoyed this episode, and want to thank you for watching. Please subscribe to Orbital Prime and click the like button along with the bell to be notified when we release new episodes.